Hello, thanks for having me. My name is Vladimir Medvedkin, and I'm working as a software engineer in Intel. Today we're going to talk about the hash library in DPDK, particularly about the predictable RSS technique. We will talk about what it is and how it can help you in your applications. So first we will discuss what problems we are looking to solve. Then we will talk a bit about how RSS technology works in hardware. After that, we will look at what predictable RSS actually is and how it works. We're also going to look at one example where Tcache could be useful, and that would be source network address translation. And finally, I'll talk about further plans. Okay, so what problems we're looking to solve? In multi-threaded environment, there could be two possible classes of problems of interest to us. First, stateful network functions, where different microflows share a single data struct, leading to concurrent access that must be serialized. For example, it could be NAT, or network stack, where two microflows, forward and reverse direction, belongs to a single bidirectional connection. In this scenario, we would like to process those two microflows of the same L core with eliminating synchronization requirements. In today's talk, we will use source NAT as an example. Second type of problems would be uneven traffic distribution across L cores, where we would like to choose which queue to handle certain flow to achieve required traffic distribution across queues. An example of that type of a problem would be packing our traffic as dense as we can to utilize as few L cores as we can, or distributing flows evenly across available queues. This could be useful both for directing traffic flows as well as for splitting fat tunnels into the smaller ones. There won't be example of that type in this talk, but this can be solved by Thash as well. Let's have a brief look at RSS. RSS is a technology that distributes incoming packets across existing queues, and it does so as follows. First, received packet is parsed by the NIC, extracting required fields to form the tuple. Then, the tuple is used as an input to calculate 32-bit toipless hash. And finally, some predefined number of least significant bits of the hash value are used as an index into intermediate redirection table to find an index in the queue to which the packet will be forwarded. Now let's take a look what do we mean by predictable RSS and how we can use it. The general idea is we want to find a partial hash collision for some number of least significant bits of the toipless hash. Moreover, we want this collision to be generated by alternating the smallest possible number of bits in the original tuple's part we're calling subtuple. Using the value of subtuple that produces this collision, we can now tell the sender which field must be set to this value for a packet to land on a specific queue. Obviously, in order for this to work, certain prerequisites must be met. Receiver must be able to change its RSS hash key. Receiver must be able to communicate this value to the sender somehow, and sender must be able to use this value as a specific packet header field. For example, in NAT we can choose translation port. In TCP/IP stack we can choose source port. In MPLS we can choose MPLS label and ask neighboring P router to use that via any control plane mechanism. The general flow of using this library is as follows. At initialization time, for each NIC we must know the following information. First, tuple layout. This is to find bit offset of the variable tuple part. Second, size of redirection table. This is because log 2 of this value corresponds to the number of least significant bits used in RSS hash value. Using this information, and optionally some random RSS hash key, the library can generate a new hash key which then has to be installed into the NIC. Then, at runtime, for any given expected tuple with arbitrary value in its subtuple field, the following needs to happen. First, we calculate hash value for this tuple and extract required least significant bits. Then, we XOR this extracted value with value we would like to have. And finally, using this XOR value, we can find bits that must be flipped in the subtuple to generate hash collision. These flipped bits are found in the pre-computed complementary table. And complementary table contains hash value to subtuple mapping, and this mapping is bijective or one-to-one because of math properties of the specially crafted bit sequence in the key. Let's have a look at example with source NAT. In this scenario, we can choose what source port to use on translation, and this port value will be found as a destination port in received packets for this bidirectional connection. For example, on the picture, both hash values have the same 6 least significant bits we wanted to have. So with 64 entries redirection table, both flows will be received by the same queue. At initialization, we configure the T-hash context, where we specify length of our RSS hash key, log2 of the redirection table size, and also optionally provide some predefined hash key. If no key was provided, it will be generated randomly. After that, a helper has to be created that will hold information about the subtuple, such as its length and offset, and both in bits. At this stage, the previously created RSS key will be adjusted to include a specially crafted bit sequence at a specified bit offset. Also, the complementary table is built on this stage. And finally, we need to install the updated RSS hash key into the target NIC. On the hot path, when deciding what source port to choose for a new translation, we need to create the reverse tuple by swapping source and destinations of the original tuple and apply address translation. Calculate the RSS hash key over this new tuple. Those two steps are omitted here. Then find which bits have to be flipped in the subtuple field. In this example, we want to adjust the original source port value. The original source port value with flipped bits then can be used as a new source port on translation. And after making such a translation, any incoming packets on the same connection will be received on the desired queue. And a few words regarding why this is working. First, Toy hash is a linear function. Particularly, this is a matrix multiplication over Galois field of two elements. So the following equation is true. Second, we must have a special bit sequence inside the RSS hash key such that different combinations of n sequences of n bits each, shifted by 1 bit from each other, are able to produce all n bit values by XORing them together. This is crucial for building the complementary table. For example, I show here three 3-bit sequences which, when XORed, can produce all possible 3-bit values. For more information, please check white paper at this link. And in conclusion, a few words about ongoing work. In this release, an RFC was submitted for an RSS hash key generating function that improves the properties of RSS hash key. The most important part of this patch series is the random polynomial calculating algorithm that improves the entropy of the hash key, since it searches all available space of applicable polynomials rather than in some predefined subset used in the current library version. This has potential to improve security for RSS, since those polynomials are used to craft special bit sequence inside the RSS hash key. And that's a good place to stop. And now I'll let my co-presenter Eimear from Huawei to take over. Thank you.
Okay, so Vladimir already spoke about essentially using the T-hash library to kind of modify a tuple by changing some of the bits, the subtuple bits in that tuple to your desired tuple. What I'm going to be talking about is more how to essentially infer directly from your L port what RxQ your packet is going to arrive on or your stream is going to arrive on. And basically to use that for actually choosing the L port that you're going to use. Okay, so first, I suppose, why is that something you'd actually want to do? Well, this kind of diagram probably looks pretty familiar to most people. This is just a very standard way to spread workload across different cores. So essentially, we assign each queue, RxQ to a core, we assign our worker thread to a core, and sort of functionally, we'll have kind of like an RxQ per core model, or like a multiple RxQ per core model. But just actually for the sake of this presentation, I'm going to pretend that it's one RxQ, one core, one app, largely to make the diagrams easier, if I'm being perfectly honest. Okay, so then as the traffic arrives on the NIC, we use the 4-tuple to index into the RETA, and that's assigned up with its RxQ. So I think actually Vladimir kind of covered that already. The reason L port is specifically important here is because generally when you're sending an outgoing connection, your endpoint is already pretty fixed. Your local IP is, you know, your destination IP, you know, and your destination port, you probably also know. So the only thing you really have control over doing is setting your ephemeral port. And so for that reason, actually choosing your ephemeral port very directly means you're going to be choosing the RxQ that the packets in your stream arrive to. So why that is important is in this split level, vertical split level kind of application, each TCP IP stack is actually independent, so they have no concept of streams initiated on other flows. So if you're actually sending an outgoing connection, you need the responses to that connection to arrive back on the core that you initiated the connection from. For receiving connections, it's no problem because RSS already steered that traffic to you, so the whole stream will arrive there naturally. One of the big problems with this, obviously, is that the more threads you add, the number of ports that are going to direct things back to your core reduces. So it's literally maximum ports divided by num threads, ports that will be available to direct packets back to your application. To work around this, there are ways to work around it, such as having multiple local IPs, but that's not always possible. You can also use like hardware offloads, like NIC flow. But again, that's quite specific, and you can't generalize that to all PCs. Okay. Oh, I had some animations here that I forgot about. Okay, so the actual project that I'm going to talk about in kind of more specific detail here is called FStack. So if you kind of, it's an open source library. It essentially uses FreeBSD as a TCP IP stack on top of DPDK. And much like the previous diagram, if you just swap out that TCP IP stack for FreeBSD TCP IP stack, it kind of works in that model with the different threads and isolation. So currently, one of the reasons that it can be difficult to scale this with a lot of worker threads is that the way it chooses the L port at the moment is essentially it'll pick an L port, it will add this RSS check function to check if that L port will make the stream arrive back on the desired RxQ. If it does, and it will loop until one matches. And then if it does, we'll look it up in the FreeBSD PCP connection table to see if it matches there, if there is a match there. If there is a match there, then we have to start the process again. So essentially, we're doing a lot of looping, and the more and more that the more and more ports get used up, the more time you're going to spend in this loop, the less ports are available to be picked even in this loop. And it starts to get quite extreme as the amount of worker threads go and the ports get used up. Yeah. Okay, so that's the background. How do we use the T-hash library then to actually derive this kind of L port hash? So Vladimir would already have spoken about this complementary table that gets created whenever you do this RT T-hash add helper. So, and the way it works is that each entry in the complementary table is the current hash XOR the desired hash, and he said it equal to the current port XOR the desired port. So what we do is essentially we take this relationship, which describes the standard complementary table, and we sort of know that our L port, the subtuple we're always going to be changing is the local port, and we just take the special case of what if the L port was actually 0. So if the L port is 0, right, anything XOR 0 is itself. So we can actually just sub in this side of the equation directly. So that means that the new hash basically becomes, we can swap in basically this 0 hash value, 0 hash value being the hash value with the L port set to 0. So the 0 hash value XOR the desired hash is going to be very directly our desired port. So that's quite an interesting relationship because what it means is actually, what we can do at initialization time is run through the entire complementary table, look up the value for every possible port, so UN16 max, and then store it. So what we do then is as long as you know the hash value of the zero hash value, that is the hash value of the L port is 0, of the flow you want to know, you can actually just do a simple lookup in the reverse complementary table and XOR it with this 0 hash value. Yeah, so the key thing here actually is that the reverse complementary table is independent actually of the other fields in the tuple. So sufficient information per flow is actually in that 0 hash. So when you're creating a new flow, and by new flow I mean per 3 tuple, not per individual port, you'll calculate that 0 hash value and then keep that. So after that, every time you want to find out what hash corresponds to what port, you simply will just do a lookup in the reverse complementary table, XOR this 0 hash. Okay, so what that does, right, is, as I said previously, one of the problems we had was the software calculation of the tuplet hash actually takes a while. You know, just by itself, it's quite a lot of cycles. So here we can actually get a really quick from L port to, or from full tuple, I guess, to hash in just this lookup and XOR. Okay. Okay, so how it's actually built from dhash. So as I said, once per kind of initialization, we initialize the dhash context as if we had a reta of UN16 max. We don't, but we can mask off the hash values later, so that it doesn't actually matter. And then we do this, as I described, we just kind of go through for every possible port. We do this RT get complement and store it in our reverse complementary table. So what we also do, because one thing along with that is that even once you've found a port that arrives in the correct queue, you still have that problem with the lookup in the FreeBSD's PCB table. So we also added as this concept of a bitmap representing whether the ports are in use or not. So basically, whenever we assign a port, we'll mark it in the bitmap. Whenever we free it, we'll free it in the bitmap. And then our loop in that sort of FreeBSD context becomes very quick, because we never expect to fail that PCB check. Okay, so this is kind of maybe a little bit more detailed on what it looks like. So basically, kind of on TCP Connect, so sort of like you're sending you're creating your connection. We'll call this RDT reserve local port function. Here you can choose like the min port possible and the max port possible. There's some flags here that I'll go into, and some data as well. So essentially, this will return you directly an L port that you can use that matches the conditions that you set in the flags and the QMask. Now, the flags, this gets a bit special because we actually allow you to assign L ports that would arrive in a different RX queue. Why do we do that? Because we've also added a flow table. I'll go into the flow table a little bit more detail in the next slide, but for the moment, you can choose to only get L ports that arrive on the core that you sent it from, or you can actually assign L ports from different cores, and we'll do this redirection later. Yeah, it's quite integrated with FreeBSD just because of the FStack is integrated with FreeBSD. So actually we call this reserve local port within TCP Connect in FreeBSD or TCP6 Connect. And we call the free, when we free the bitmap and everything, actually in the destruction of the PCB, in the PCB destructor. The reason we don't do it at socket and socket creation and release is TCP time wait. So things can still fail the PCB lookup if you try and add it before the PCB is expired, not just the socket. Okay. This one, okay, I thought that one had animation, but it doesn't. Okay, so the flow table, there's a bit more detail on that. So this is like if you imagine the RX path, we have this classify function. And what that does is it works on an array of packets, and it looks up and sees if there's an entry in this flow table, which is just essentially a hash table. If there is an entry, that means it needs to be redirected. The core that it will be redirected to is actually this kind of UData that we had here. And if there's no entry in the float table, it means that it was a locally assigned queue and we can just send it directly ahead to the thread we need. Okay, so the gist here is that basically we can get over this problem of local ports being limited by the number of threads divided by the number of, the number of ports divided by the number of threads, because we can actually borrow ports from other cores and we just redirect them here at RX. And it's just actually, we use, again, did I say this later? We use FreeBSD's own kind of built-in queues for this, these dispatch queues, but they're very basically just RT rings. There's nothing actually particularly special about them. Okay, so that's basically it. So the three kind of problems we had were we spend quite a long time in that software toplet task calculation. 2, then we have this issue with the PCB lookups, and 3, we run out of ports. So the Thash library lets us solve the time spent in hash calculation by this reverse complementary table. The bitmap helps us always never fail the PCB lookup, and then this flow table allows us to spread out our ports a lot more evenly. Okay, so the interesting bit, results. So we've set for IPv4 and IPv6 here. Essentially, you can kind of see the blue line at the bottom here is, in both cases, the one with RDT off entirely. And you can see what happens is, essentially, as you add the number of workers here, that's the number of threads, we actually get this quite terrible scaling problem here where performance actually starts going even down, not just not scaling linearly, it's actually getting worse. Whereas RDT enabled in both cases, so one of these is all local, where we only accept, we only use L ports that would already be RSS'd to the core, and one is all remote, because it's like the worst case scenario, essentially, where we, for some reason, decide that we'll only choose RX queues that are not our core, so we're always kind of doing that redirection on RX. And you can see that it's actually, even with redirecting every packet on RX, I mean, it's worse than not doing that, but it's still much more linear. It's much closer to linear, I should say. So we expect to see that performance curve grow better. Yeah, no, it's back. Okay, this is with Nginx, so just maybe a more kind of real-world example. Just for context, this was done with kind of our own kind of TCP client. All it does is kind of create a connection, send a packet, and then close the connection. Here with Nginx, you can also see this is with 16 workers. You can see that, like, as we increase the amount of kind of concurrent requests, we don't see this with RDT enabled. We don't see the same kind of fall off. Yeah, so that's Nginx. And yeah, that's kind of mostly it. So thanks obviously to Vladimir, who wrote the Thash library, on which the kind of majority is based on, and then everyone else on the team in Huawei who also worked on this. So, questions?
So the mic's in the back now. Hello. Have you thought at all about the security implications of all this? Because I know that the Linux kernel goes through a lot of work right now to make sure that the ephemeral ports are truly randomized, non-predictable, because there's a whole bunch of both TCP attacks and DOS attacks that depend on not having knowledge about what's at the other side.
I'm not sure you can get rid of the predictability, because, like, for a fixed endpoint, so source test, like if it's using RSS, then the local ports, the ephemeral ports, are always going to end up in it being assigned to a certain RX queue.
So there's two classes of attacks. One is DOS attacks, where if I know your RSS key, I can hit you with a stream of SYN requests, and I can make them all show up on one core. And perhaps I also know that that service I want to hit is on that core, and I can swamp that core and make it fall away. So
I think
the way
Hi,
they
Steven.
solve that is generally to try to make sure that the RSS key is random and not known.
Yeah, so we're not changing anything about how RSS behaves in that sense. Like whatever the whatever the RSS key is, the ports will be distributed in that sense anyway, like by RSS. So we don't change that at all. The only thing we're adding with the redirection table, or our redirection table, is to do this redirection after RSS.
Okay. And the other attack is
Uh,
typically
Steven,
if
Steven,
I know
can you
from
hear
an
me?
existing connection what the next port that's going to be used by an application is, I can man in the middle and get in and basically slide in ahead of that connection and and play with its stream to intersperse data.
So we do actually choose our next port kind of randomly. I would
Yeah.
say that was more for performance reasons than actually for
Okay, so people do
security
think
reasons.
this is a stupid low bar security thing, but unfortunately the real world people depend on it, which is
Well, kind of an interesting thing about this is because we redistribute the packets after RSS, in fact, packets will arrive on cores that would not be predictable via straight RSS.
Okay.
So,
okay.
in a sense, it's more secure. Oh, Vladimir would like to speak. So,
Yeah. Can you hear me now?
yeah,
Hello? One,
yeah,
two,
we can hear you.
1, 2, 3. Can you hear me now?
We can hear you.
No? Yes? I wonder about audience. Okay, good. Stephen, this is a really good question about RSS security. So I wrote about this problem in my last patches for about Thash library. So the rule of thumb should be generate RSS hash key using random, then adjust it using Thash library new API. Yes, this API. So you don't need to generate the whole key using Thash library because in this way, entropy of the key wouldn't be enough because now entropy will be limited to the Kolmogorov complexity of the bit string. And Kolmogorov complexity of the bit string limited with the log2 of number of possible polynomials, which is not so much. So first, generate random RSS hash key, then improve it using this library, but improve it in a very limited way. And of course, obviously, don't use some predefined, well-known RSS hash keys because it's not secure. And DOS attack, as you mentioned, is possible. Yeah, that's it.